Hi Trigoners. So this is the first idea that you need to learn in our sequences chapter. I'm on sequences day 1, part A. A sequence is just a list of numbers. And you always have natural number inputs. Sometimes they can be whole numbers, so you can have an input of 0, but classically we start with n being equal to 1, and then we increment by 1. So when n equals 1, we get 2. When n is 2, we get 4. When n is 3, we get 6. And when n is 4, we end up getting 8. So that represents the first 4 terms of this particular sequence. Number 3, start with 1 again. So a sub 1 is equal to 2 cubed, which is 8. A sub 2, listen to how I say that, is equal to 3 cubed is 27. A sub 3 is 4 cubed is 64. A sub 4 is 5 cubed is 125. And so you have written the first 4 terms here. Sometimes people like to separate them with a comma. Number 5. This one is a little bit more interesting because you have this -1 to the n plus 1. And just work through the problem till you can start to see a pattern. So this becomes a 7 over here, and -1 to the power of 2 makes this a positive number, so we have a positive 7. A sub 2 this term is 12, but if you notice this exponent right here is 3, which makes this negative. This is a negative value, so we end up having -12. A sub 3 will be a positive 1 times 17, and a sub 4 is negative, because you'll end up having an odd number up here, times 22. So this is what we call an alternating series, because the numbers alternate from positive to negative. Find the 100th term of the sequence in number 4. The sequence in number 4 is a sub n equals n minus 2 over n plus 2. Double check that, yeah. And what's nice about this kind of formula is that I can plug in 100 and get the answer right away. That's what we call an explicit formula, and that means that there's other kinds of formulas too. So we're going to investigate explicit formulas and also other ones, but the 100th term is simply when you plug in 100. So that's 98 divided by 102. Number 11, write a general term for a sub n. One thing that I want you to see is that these numbers are going up by 2 every single time. And that represents linear growth. And really you can just make the equation of a line here. The slope ends up being 2, and you can use your point slope form that we've used before. So if this is your first term, your second term, your third term, your fourth term, you can say y minus 11 is equal to 2 times x minus 1, which means that a sub n is equal to 2 times n minus 1 plus 11, and that would represent an explicit formula. Notice that number 12 is exactly the same magnitude values as number 11, but you have the alternating sequence. So if this is your first term, second term, third term, fourth term, then you're going to use the exact same base, and then you have to make this sequence alternate. So if I have a -1 here and I raise it to a power of 1, that should be a negative, but it's actually not in the sequence. Therefore, I have to make it be a positive, so I add 1. And you can double check by doing the next term. 2 plus 1 is 3, which would make that value negative. Number 13, remember that we're starting with a 1, a 2, a 3, and a 4. This is an assumption, really. You could start sequences with zeros, 1, 2, 3, etc. But generally in our class we'll just start with 1. And if you notice, all of these numbers here are just 1 more than the term being plugged in. So we'll have an n plus 1. And these numbers down here are 4 more than the terms that were plugged in. Okay, so going back through all of these problems, I'd want you guys to try them. I wish we had had more time in class to be able to talk these through. But so just try them and just see how well you do. It's really all about patterns and coming up with a pattern for being able to plug in numbers. I'm going to move on to sequences day 1, part B. So this is us getting into special types of sequences. Sequences can be really anything, like just any pattern of number, and sometimes they represent situations that really have no pattern. So the absence of pattern also can create a sequence. But then there's also types that have a very specific pattern, and that's what we're about to explore. So looking at case number 1, term 1 has 1 black triangle, term 2 has 3, and term 3 has 9. And if you can see, you're always multiplying by 3. So if you went to term number 4, there would be 27. And if you multiply by another 3 to get term 5, there would be 81. We call this kind geometric. Geometric and exponential are synonymous. In number 2, the volume represents 1 cube. The next term is 3. The next term is 5. This time you're adding. So the next case would be 7, and the next case would be 9, because you're adding 2. We call any time that you are adding or subtracting, we call those arithmetic. So geometric will multiply or divide, and arithmetic will add or subtract. As a connection to our class, this is exponential and this is linear. Both 2 different functions that we've already studied, so this is just an extra little step. All right, so we have some examples here. Number 3, I see that my pattern is always adding 2. So I would consider this one to be arithmetic. Listen to how I say that, arithmetic. In number 4, we're dividing by -2, so I would get a positive 1/4, a negative 1/2, a positive 1/16. I consider this to be geometric because I'm always dividing by the same number. Number 5, adding 7, so we get 36, 43, and 50. And then number 6, it's clearly a pattern. These are perfect squares. But because you're not always adding the same number, like here, this is adding 5, then adding 7, then adding 9, etc. You're not adding the same number, and you're certainly not multiplying by the same number. So I would consider this to be neither an arithmetic or geometric sequence. It's still a sequence because there's a pattern there that exists. It's just not part of our definition. So an arithmetic sequence has a common difference, and we classically call that common difference D, and a geometric sequence has a common ratio, and we classically call that R. So now we're going to dive into arithmetic sequences. We have a term, a sub 1 is 55, a sub 2 is 49, a sub 3 would be 43, and if you notice, you're always subtracting 6. So here in my process, I would be taking 55 and I'd be subtracting 6 0 times. For this one, I subtract 6 2 times, etc. So when I get here, it's a sub 1 plus d times 1, a sub 1 plus d times 2, etc. So take a second and fill in these blanks and see if you can come up with our general explicit formula. All right, so this is what I got for this column. And the important thing to notice is that the number that's always going here is always one less than the term number. So my explicit formula for an arithmetic sequence is always this right here. And it really is just like point slope form with that y value moved over. So I'm going to recap that here. Okay, let a sub n be an arithmetic sequence. A sub 1 is 25 and a sub 2 is equal to 16. That means my d value is equal to 9. The explicit formula is 25 plus 9 times n minus 1. A sub 15 is equal to 151. Number 2, find the d value. You can use your equation that we gave to you. So a sub n in this case is a sub 7 is a sub 1 plus d times n minus 1. And so you have everything there except for your d value. Negative 12 is d times 6, therefore d is equal to negative 2. But also remember that arithmetic sequences are linear. And really this just represents the slope, or like two ordered pairs on a line. So you can also just use your slope equation and also get negative 2. Your explicit formula will be 36 minus 2 times n minus 1. I will let you find a sub 32. Number 3 is part of the work that I want you guys to do without me. A recursive formula for an arithmetic sequence is always in this pattern right here. So we need to understand what each of these elements represents. So a sub 1 is your start, and a sub n minus 1 is considered to be your previous term, and then your d value is that common difference. So before we move on to another sequence, let's understand from like a basic sequence. So let's take 1, 3, 5, and 7. I would say that this is the start. I would say that my common difference is always plus 2 to go between terms. So d equals positive 2. And then I can get this term because I know that if I took the previous term and added 2 to it, I would get here. Or I could figure out this term because I know this one and I add 2 to it. So remember that if this is term 1, term 2, term 3, term 4, how can I come up with this number? I can subtract 1 from the next one. So every recursive formula needs 3 parts. You need to have a starting position, this previous term element, and also how the pattern continues. So in number 1, a sub 1 is 25 and a sub 2 is 40. I think d is equal to 15. Here's your recursive formula. A sub n has a starting value of 25, and every a sub n after that will add on 15. This part is equally important because it tells you for what other term numbers you're able to find. If this is your start, the next term that I can find is 2. And that's exactly why I had this up here. A sub 4 is more complicated to find in a recursive formula because you need a sub 3. But a sub 3 needs a sub 2. And a sub 2 needs a sub 1. So this ends up being 25 plus 15 times 3, and that transitions us back into the explicit formula. So 25 plus 45 is 70.